This is the 6th section of chapter 1 on algorithms, and this section is about the order of an algorithm. Now, different algorithms take different times to work through. Typically, these algorithms like bubble sort, quicksort are done on computers, and we want to know basically how long an algorithm is going to take to complete, let's say on a computer or even manually. Now, if we know how long an algorithm takes to complete, let's say 10 items of sorting, and we want to know how long it takes to complete 100 items, it may be that the link between the time and the number of items may not be linear. It may be a quadratic relationship, or it could even be a cubic relationship. But what we do know is that the time taken to complete an algorithm will be proportional to the number of items. Let's put number of items. Now, that may be a linear relationship like this, or it could be that the time is proportional to the number of items squared, which means, for example, if you were to double the number of items, the time would take 4 times as long to complete the algorithm. Or it could even be cubic or quartic. We'll just finish at cubic here. So the number of items cubed will give you the time taken. So it's not always a linear relationship. So for example, if the number of items was doubled, it would take 8 times as long to complete the algorithm. Now, if we know the type of relationship it is, we can just use the techniques we use for direct proportion from GCSE to answer these types of questions. And so we could say T equals Kn. So here where T is time, and I'll use N for the number of items or the number of letters or the number of numbers. Here it would be T equals Kn squared or N squared K. And here it would be T equals Kn cubed. Now, whether it's linear or quadratic or cubic, this is called the order of the algorithm. So the order, or it could even be called a complexity, or the size of the problem, is called the order of an algorithm. And this order can be linear, it could be quadratic or cubic. As I said, it could even be quartic, but at this level we only really need to recognize these types of order. And the time taken to complete the algorithm can be called the runtime. So the time taken to complete the algorithm can also be called let's sort my writing out, also called runtime. So you might see that phrase there instead. Now, one note is that when we work out the runtime from the number of items, these are only estimates. Okay, so estimated time, it doesn't mean the algorithm is going to take exactly that time to calculate. We've got an algorithm that's defined by this flow diagram here, and we need to determine what the algorithm does. So we could just input lots of different numbers to see, but let's have a look through the flow chart and see if we can work out for different values of n what happens to those numbers, where do they end up. Right, so first of all we import a number n, where n is a integer greater than 2, and then we say let a equal 2, and then we say is n divisible by a. Okay, so whatever number I type in the first question I'm asking, is it divisible by 2? If it's yes, it goes over here. So we know that all even numbers are going to end up here. Okay, let's keep going round. Then whatever number it is, we ask, is a, for the first time round, is 2 less than the square root of the number that I've typed in? If it's not, then we go to here. If it is, then we go around the loop again. Now what happens here? So then I increase a by 1, now it's 3, and I'm asking, is the number that I had divisible by 3? So let's focus on what type of numbers are going to end up here. So we said even numbers. Then if we go around here again, it's going to be numbers which are divisible by 3, then divisible by 4, and then 5, and then 6, and a is going to keep increasing until this question gets answered no. So basically, if any number is divisible by an integer greater than or equal to 2, it's going to end up here. So it's not just even numbers, it's not just numbers which are divisible by 3 or 4, it's actually going to be any number that is divisible by an integer greater than or equal to 2. That means then that any number that isn't divisible by an integer greater than or equal to 2 is going to end up here. And these must be the prime numbers. Prime numbers are those numbers that are only divisible by 1 and themselves. Now we're starting from a equals 2, so prime numbers are not going to end up here. And we never get to find if a number is divisible by itself, because basically when the value of a is greater than the square root of the number, we stop. So let's just check it with a couple of numbers and see if that works. So let's say, for example, I put in the number 9, which I know isn't a prime number. What happens? Well, first of all, I say, is 9 divisible by 2? No. Is 2 less than the square root of 9? Yes, it is. Okay, and that a becomes 3. Is 9 divisible by 3? Yes, it is, so it ends up over here. Okay, let's try a number that we know is prime. So let's say 17. So 17, is it divisible by 2? No. 2 less than the square root of 17? Yes, it is. A is 3. 17 divisible by 3? No. 3 is still less than the square root of 17. Then 4, is 17 divisible by 4? No. Is 4 less than the square root of 17? Yes, it is, just. 8 is 5. 17 is not divisible by 5. Is a less than the square root of 8? Is 5 less than the square root of 17? The answer to that question is no. So we end up here. So 17 ends up here. So that's just a couple of examples, but I could basically say what the algorithm does. It outputs non-primes to A and primes to B. So it sorts them. It sorts all the non-primes here and the primes here. Part B asks for suitable output boxes for box A and B. So A, I would put something like n is not prime or non-prime, or the input is not prime, and B, n is prime, or the input n is prime. And part C asks for us to determine the order of the algorithm. And that's basically how many times we go around this loop. And how is that decided? Well, that's decided by whether A is less than the square root of n or greater than the square root of n. So the number of times we go around this loop is the square root of n. The processing time is the square root of n. So we can say that the order of the algorithm is root n. Order of algorithm is root n. Now this is just an estimate. It's not exactly root n, because for some numbers, the number of times you go around isn't exactly the square root of n. So for example, when we had 9, which happens to be a square number, so is 9 divisible by 2? No, it's not. So we have this processing time once. Is 9 divisible by 3? Yes, it is. So actually we only go around this loop once, but when we get to 10, for example, so it's divisible by 2, it ends up here. So some numbers, the processing time is going to be very short, even numbers. For square numbers, the processing time actually is going to be shorter than the square root of n. It all depends whether that square number is divisible by a number smaller than its square root. So for example, 36 is even, so it will end up over here. It's the primes that are going to take up all the processing time, because we've got to keep going around that loop. So the order of the algorithm is the square root of n, which is basically like the longest processing time we're going to have, and that's going to happen with the primes. Okay, a given list searching algorithm has linear order. Okay, to search a list with 500 values, the algorithm takes approximately 0.036 seconds. Estimate the time taken by this algorithm to search a list containing 1,250 algorithms. Okay, so if it's a linear order, that means the time taken is proportional to the number of values. So the time t is equal to k times the number of values. Okay, so here n times for the equals the number of values, and t is the time taken. So a linear order, so it's going to be a linear proportion. So we want to find k. So 0.036 seconds is going to equal 500k. So k is going to equal to 0.036 divided by 500. That gives us a value of k equal to 7.2 times 10 to the power of -5. And estimate the time taken. Remember, this is only an estimate. It's not going to be the exact time. Time taken for this algorithm to search a list with 1,250 items. So our equation is going to be t equals 7.2 times 10 to the -5 n. So we just replace the number of values with 1,250 times 1250. We get a value of t of 0.09, and that's going to be seconds. So here's our answer. Okay, so we've got a bubble sort here that has quadratic order. So we need to be thinking of this type of thing, like this. Given that it takes a computer 0.2 seconds to sort a list of 1,600 numbers using a bubble sort, estimate, so remember these are only estimates, the time taken to sort a list of 48,000. Right, so our time is proportional to the number of items squared, which means t equals kn squared. using the values that we've been given, 0.2 equals k times by 1600 squared. K equals 0.2 divided by 1600 squared. So that gives us a value of k of 7.8125 times 10 to the power negative 8. So our proportion relationship becomes the time is equal to k 7.8125 times 10 to the power negative 8 times by the number of numbers squared. So now we can just plug our numbers in to find the time. So the time is going to be 7.8125 times 10 to the power negative 8 times by the number of items now is 480,000 squared. So time in seconds gives us 18,000 seconds. So you might want to see what that is in maybe hours or days. So if we divide that by 3,600, it gives us an estimate of 5 hours to complete that task. Okay, then part B, comment on the suitability of the bubble sort for sorting large data items. Now, if you double the size of the number of items, you increase the time by a factor of 4. If, let's say, for example, you increase the number of items by a factor of 5, then the time is going to increase by a factor of 25. The time will increase by this factor squared. Now you can see that for sorting less than 500,000 items, it took 5 hours. And some databases contain millions and millions of items. So let's just have a look. For example, if I had 1 million items, time taken to sort 1 million items. I'm not asked for this, I'm just showing you what happens. That is going to be t equals 7.8125 times 10 to the negative 8 times 1 million. Now for t, that would be 78,125 seconds. That doesn't seem too bad. Well, actually, if you divide that by 3,600, you get 27 or 21.7 hours. That's a long time, a lot of computing time. So I will say that since the time taken increases by a factor of the number of items squared, this algorithm, the bubble sort, is not suitable for sorting large data items or sorting large data items. You should now be able to complete exercise 1F on page 24 of the textbook. So quick recap. This was all about working out the order of an algorithm, sometimes calls the complexity or the size of the problem. And we were working out the time, what can be called the runtime of the problem. And the relationship between the time and the number of items can be linear, it can be quadratic, or it can be cubic, where t is the time taken and n is the number of items being sorted.